One of the most important sustainable development goals for the UN is clean water and sanitation. Our slides will be discussing the issue and a potential solution using treatments and engineering applications. In this slide, we will be talking about the problem, some statistics and facts about the sanitation issues we face. According to Healing Waters, 850,000 people die every year due to the lack of clean water and sanitation. Basic sanitation include the following according to the CDC: facilities for human waste, ability to maintain hygienic conditions, garbage collection and hazardous waste of management, and of course, clean water treatments. More than just being clear, it's safe and uncontaminated. This fundamental right is not only killing thousands, but the disregard to the issue is causing the loss of millions of dollars. Approximately $260 billion are lost globally. Not having access to these rights causes more problems, and it ripples through society, costing more than the solution would. 1 out of 3 people in the world don't have access to clean drinking water. That's the equivalent of 2.2 billion people. At least 2 billion people worldwide have to drink water contaminated with feces. 4.2 billion people do not have safely managed sanitation services, more than half of the world's population. 32% of the world's population lacks basic sanitation facilities such as toilets. 673 million people have no option but to defecate in the open, in street, behind bushes, or in open bodies of water, leading to the assault of innocent adults and children. In this third slide, we will be seeing pictures of how these issues have affected the society. On the first picture, we are going to see children gathering dirty water because it's the only thing they have access to. Another shows a child drinking water from a community spout. The last picture shows water samples being taken to test if it's usable. Unfortunately, 6,000 children die daily from water-related diseases, according to the UN. Clean water and sanitation is not just a foreign issue. In 2014 to 2016, the public water supply of Flint, Michigan was polluted with hazardous levels of lead and bacteria. This issue was projected nationwide, and it caused multiple deaths and outbreak of Legionnaire's disease, which affects the lungs. No one is immune to this issue. It's simply more prevalent in certain locations.
The next slide shows the 7 stages of water treatment. If you don't know what a water treatment is, it's a facility where water is sourced and treated to remove chemicals and hazardous particles in order to meet safe drinking and sanitation standards. It must also meet non-corrosive standards so it doesn't damage pipework during delivery. This utility distributes safe tap water to communities globally. The treatment can vary depending on community and the initial quality of the water. The steps are as followed: screening, aeration, coagulation and flocculation, sedimentation, filtration, chlorination, and supplementary treatment. This slide is a visual representation of the 7 steps and how they work. We will briefly explain them all. So, you begin with screening. As shown in the first picture, in order to protect the parts of the treatment plant and to aid the efficiency of the process, the water is initially processed through a big screen that filters the big corrosive materials like rock, twigs, debris, etc. It's sort of like a big strainer. They are very fine and thin, while others are more spaced. The next step is aeration. So, aeration by definition is the introduction of air into a material. In this case, the water is aerated in steps to take in oxygen from the air. This helps purify the water in order to stop soluble gases like carbon dioxide and hydrogen sulfide. Soluble meaning they can dissolve into the water and contaminate it. Since both are acidic, it stops from making the water corrosive, so it doesn't damage the plants or pipe. This process also helps get rid of iron and manganese. These elements affect the taste of water and can also stain clothing. However, once they are insoluble, meaning they won't dissolve, it can be filtered out of the water. In certain cases, when the algae in the water, it can cause the growth and reproduction of more. However, aeration, also known as pre-chlorination, can help treat this before the main stages. The next step is coagulation and flocculation. This is meant to remove extremely small particles less than 1 micrometer in size. The particles have a negative charge. In order to neutralize them, a chemical called a coagulant, has a positive charge, is added to the water to neutralize them. As shown in the picture, there are stages of propellers that the water goes through. When passed through this tank, these high-speed propellers disperse it. As the particles are neutralized, they combine, forming big particles called flocks. Two of the most commonly used coagulants are aluminum sulfate and ferric chloride. Once the flocks are formed, the water goes through the steps flocculation. The water is put into a bigger tank, and a big paddle is used to stir it and basically form big flocks. The different speeds allow it to go through the water without breaking, while giving them the proper space to group and compartmentalize. The next step is sedimentation. This step is meant to settle the flocks after they are formed. This tank has zones at the bottom called sludge zones. The flocks slowly set at the bottom to form sludge. It is then removed and disposed of. The remainder is the water minus the flocks. The next step is filtration. Once the flocks are gone, the water is passed through filtration. They are run through different beds of multiple materials such as sand and gravel and varying pore sizes. This traps bacteria, parasites, and viruses, but also dissolves particles like chemicals and dust. The reason this didn't get removed during sedimentation is because it doesn't have a charge, so it can't flock. Additionally, carbon filters remove odor and the water. Once the solids are gathered, they are backwashed. During this process, clean water and air is pumped back up the filter to collect the impurities that may have been trapped. The backwash is pumped to the sewage system if there is one. If not, it can be pumped back to the original water source. Sometimes plants use reverse osmosis. It's another method that removes particles, often used when recycled water is treated. This works by using pressure to pass the water through a semi-permeable membrane that blocks molecules from passing through depending on charges and size. So the following step is chlorination. After sedimentation, one of the final sanitation steps is to use disinfectants such as chlorine, chloramine, and chlorine dioxide to terminate pathogenic microorganisms. One of the cheapest options to use is sodium hypochlorite. After it reacts with the hazardous microorganisms, the remaining chlorine lives in the water until it reaches the consumer. This allows for other pesky bacteria that may enter on the way to be controlled. The World Health Organization guideline advises that the amount of chlorine that remains in the water be 0.5 milligrams of chlorine per liter of water. Once it's fully disinfected, the water is dispersed to a facility where it is then sent to consumers. The final step is supplementary treatment. This step is often optional, but it does provide a lot of benefit to consumers. It's meant to treat and enhance the water for well-being of its consumers. For example, the World Health Organization adds fluoride to water. This actually helps prevent tooth decay.
Alright, so now we're going to elaborate on some of the potential solutions that can be implemented on a broader scale in order to deal with the issue of unclean water all around the world. Some of these solutions include membrane separation, solar water disinfection, ceramic filtration, and biosand water filtration. Membrane separation consists of a process of pushing high amounts of pressure in a sample of water through a series of membranes using methods such as reverse osmosis and nanofiltration to remove pollutants and bacteria from the water. These advanced technologies are capable of removing everything from salts and heavy metals to viruses and pharmaceutical residues. They're commonly used in desalination plants, hospitals, and emergency water supply systems. Solar water disinfection is a brilliant example of the simplicity of water filtration, as all it takes is about 6 hours of sunlight in a clear plastic bottle to remove common pathogens such as E. coli, Malaria, and Giardia. It's one of the most economically viable methods, used in over 30 countries, and is recognized by the World Health Organization. Ceramic filters is another economically viable method of water filtration, often made from locally available clay that has tiny pores that can trap bacteria and parasites. It consists of using a container filled with layers of washed sand and gravel, which then has fresh water poured over it to filter the pathogens to make clean drinking water. They are reusable, long-lasting, and ideal for household use. Finally, biosand filters offer multiple layers of protection. The top layer, called the Schmutzdeck, is biologically active and consumes pathogens. Beneath it, layers of sand and gravel provide physical filtration. These filters are sustainable, require minimal maintenance, and can last for years.
The first application of engineering is clean water supply. This includes infrastructure that delivers safe drinking water to both urban and rural populations. Without engineered systems, including pipelines, pumping stations, and treatment facilities, natural ecosystems simply cannot provide the scale of access modern society requires. Wastewater management and sanitation are among the most essential services for public health. Treatment plants remove contaminants more efficiently than natural systems, protecting people from disease and ecosystems from pollution. In cities, centralized facilities treat millions of gallons of wastewater daily, ensuring it is safe to return to the environment or reuse in agriculture and industry. Irrigation for agriculture. This works by having systems like drip and sprinkler irrigation improve water use efficiency by delivering water directly to plant roots, minimizing waste and maximizing yield, especially in regions with low rainfall or unreliable ecosystems. In the area of flood control and risk management, engineered systems like dams and drainage channels protect communities from increasing weather extremes. These structures help balance flood protection with sustainable land use and development, especially in storm-prone areas like Florida. Lastly, urban infrastructure now combines traditional gray solutions with innovative green ones. Stormwater management, runoff filtration, and future water demands are handled by integrated systems that use nature-based strategies, like rain gardens and green roofs, alongside conventional engineering. Another technique, the PUR water purifying sachet, is a simple innovation designed for communities without access to traditional water treatment. Each sachet contains a powdered formula that can clean up to 10 liters of dirty or contaminated water. It works by using coagulation and flocculation, clumping together dirt and pathogens, which then settle to the bottom of the container. Within about 30 minutes, the water becomes clear and safe to drink. PUR sachets are lightweight, easy to use, and incredibly affordable, making them ideal for disaster relief, rural areas, and emergency situations where clean water is urgently needed. Desalination is a powerful solution for regions where fresh water is scarce. It works by converting seawater or brackish groundwater into clean, drinkable water. With the help of advanced membrane technologies like reverse osmosis, modern desalination plants can remove salts, heavy metals, and other contaminants, turning previously unusable water into a safe and reliable resource. Engineering also plays a role in decentralized systems, which are especially important in underserved or remote areas. These small, modular treatments allow for localized water purification and waste treatment, helping relieve pressure on centralized systems and expanding access. This final message is directed to the Tampa Department of Public Works and the Water Department. You already have done important work in building and maintaining water systems that serve hundreds of thousands of people, but as Tampa grows and as climate change and resource challenges intensify, we encourage you to lead the way in sustainable innovation. We urge you to pilot new filtration technologies such as biosand or ceramic filters to support community resilience and emergency preparedness. Expand Tampa's investment in green infrastructure to handle stormwater more effectively and enhance environmental quality. Consider implementing decentralized water and wastewater systems in underserved neighborhoods to increase accessibility. And most importantly, invest in public education to raise awareness about water conservation, household safety, and hygiene.
Thank you for listening and watching.